Welcome to the E-Pathshala lecture series on computer science for postgraduate students. This is the 6th edition of in the lecture series on computer graphics and visualization. So, today let us recollect what we have already learned in this subject, and in the last session we talked about transformations, the basic transformations, the translation, rotation and scaling. And let us continue the lecture series with the today's session on composite 2D transformations. To start with, composition is something like you are actually merging up a series of transformations. Composition is an important aspect of computer graphics. So, in this composition, what we do is we take a series of transformations and we combine them into what is called a composite. Okay. The advantage of having a composite is to multiply the initial coordinates, get the final coordinates straight away at one stroke. So, having a composite matrix is so advantageous, it reduces the number of matrix operations. If you recollect, we talked about homogeneous transformations and homogeneous coordinates and coordinate system. In homogeneous coordinate system, any transformation matrix is represented as a 3 by 3 matrix. So, if you recollect, the translation matrix, the rotation matrix and scaling matrix represented in homogeneous coordinates, it has got 3 coordinates and it is a 3 by 3 transformation, each is a 3 by 3 transformation matrix. So, what we are going to do here is, in the real world scenario, we have more than one transformation that is applied on an object in succession. So, at very high speeds, more than one transformation is applied on objects. For example, if you take the Tom and Jerry like cartoons, if you take say animation movies, the famous animation movies. So, many transformations happen in succession. For example, a translation happens, a rotation happens, a kind of shape change happens, a kind of say reflection happens, a kind of what is called a scaling happens. So, many of the transformations are applied in a succession on the same object. So, let us see the advantages of these composite transformations. So, like the fundamental advantage is it reduces the number of matrix operations, and another major advantage is it avoids intermediate storage. So, whenever you have to say, for example, whenever you perform a transformation, you store the result in an intermediate storage, say for example, in a memory storage, and again use that for the next transformation and store the intermediate result somewhere. So, till you finally finish all your transformations. So, then doing so, instead of doing that, here what we are doing is we will be performing a composition of all these transformations, and then we will be multiplying, getting a composite matrix, multiply the initial coordinates, get this final coordinates straight away. That is the fundamental advantage. So, let us look at the first example that talks about a composite transformation. The example is about 2 successive translations. Assume that you have to perform 2 successive translations, that is a translation and again a translation. So, let T1 be the first translation with the components Tx1, Ty1, let T2 be the next translation Tx2 and Ty2. So, now a point P is there on which these 2 translations are applied in succession. So, now what will be the end result or what will be the end coordinates? For that what we do is, you can see here as the solution starts with, first T1 is applied on P as T1, Tx1, Ty1 multiplied with the point P. So, we know that in homogeneous coordinate system, a point P is represented as x comma y comma 1. Okay. So, the translation matrix T1, whose components are Tx1 and Ty1 multiplied with the matrix P with the point P, which is a matrix, gives another 3 by 1 matrix. Okay. So, what we did is what we wanted to do now is we have to apply T2 again on the result. So, that is, see this curly braces here in the second step, P dashed is equal to the final coordinates are T2, Tx2, Ty2 multiplied with T1, Tx1, Ty1 multiplied with P. Please focus on the curly braces, the red ones. The red ones indicate that first T1 is applied on P, and on the result, so which is a 3 by 1 matrix, we are applying T2, and the final result is stored in P dashed. Now, if you see this step here, that is, we are writing the same equation, but with just the braces alternatively placed. You see this curly braces here, the red ones particularly. In the previous slide, we have the red curly braces for the T1 into P, for T1 into P, and now we have just altered the curly braces so that P is independent and kept aside, and T2 and T1 are multiplied, and the resultant is what is called the composite matrix. And first do this multiplication, then multiply the resultant with P, straight away get the P dashed. So, the essence of this is to perform a series of transformations, basically here translations, and the resultant is actually a composite transformation matrix, and that is multiplied with the P to get P dashed. So, if you see the matrix equivalents for this notation, P dashed is x dashed y dashed 1 in homogeneous coordinates is equal to 1 0 T x 2, 1 0 1 T y 2 and 0 0 1 multiplied with another matrix T 1, 1 0 T x 1, 0 1 T y 1 and 0 0 1 multiplied with the point x y 1. Keep the point x y 1 aside, just multiply these two transformation matrices, what you get is the composite matrix. The composite matrix is just exactly looking similar to that of a translation matrix. Now, with the third column having two terms, which are the addition of the two x components and addition of two y components. So, basically applying two translations in succession is equivalent to shifting the object twice, that is applying T1 first and then T2 next. So, the object is at a new position. So, two successive translations are additive. So, that is the conclusion. So, coming to two successive rotations, imagine you are performing a rotation on an object first and then applying another rotation on the resultant object. So, that is first it is rotated and then again it is rotated by some other angle. Let theta 1 be the rotation angle for the first rotation, let theta 2 be the rotation angle for the consecutive second rotation. So, assuming all these rotations are positive, that is counterclockwise rotations, as we know very well that counterclockwise rotations are positive, clockwise rotations are negative. So, if you remember the standard rotation matrix, so we have converted this notation into equivalent matrix, x dashed y dashed 1 is equal to r 2 theta 2 cos theta 2 minus sin theta 2 cos theta 2 0 0 1 and 0 0 1, and similarly cos theta 1 minus sin theta 1 sin theta 1 cos theta 1 0 0 1 and 0 0 1. When we multiply these two, the resultant is a composite rotation matrix, and if you observe this carefully, the angles are actually added up here, theta 2 plus theta 1, theta 2 plus theta 1 and so on. So, the resultant composite matrix is actually additive. So, we can conclude that two successive rotations are actually additive. So, in the previous case we did two successive translations, they are also additive, and two successive rotations are also additive. And one important thing is that you should observe this reversal of transformations that are applied. First it is R1, then it is R2. When you are writing them in an order, it is R2 into R1 into P. So, please understand that because we are performing first R1 on P and then R2 on P. So, R2 into R1 into P. So, that is the sequence. So, similarly that if we look at two successive scaling operations, if we want to perform, that means you are scaling an object first and on the resultant scaled object you are performing again another scaling, say S2. So, S2 and S1. So, this should be actually S2, this is S1, sorry, this is again this has come as S2, can correct this as S1. So, let S1, Sx1, Sy1 be the scaling matrix first applied on P, and on the resultant we are applying S2. So, this can be written as S2 into S1 into P. So, you can make the correction here, this is S1. Okay. So, Sx2 0 0 0 Sy2 0 0 0 1 Sx1 0 0 0 Sy1 0 0 0 1 into Xy1. Just keep this aside, the point aside, multiply the two transformation matrices. What you get is a composite, but unlike the previous cases, the composite transformation matrix for two successive scaling operations is actually multiplicative. That means, the two scaling factors actually get multiplied. So, the resultant is a scaling matrix whose coefficients are values are multiplicative, scaling values are multiplicative. So, that is about basic basic operations that we have performed, two successive translations, two successive rotations and two successive scaling operations we have performed. But in the real scenario, we generally do a series of transformations, and they are generally more in number. Okay. So, let us take a scenario which we call this as a complex transformation. Let us take the example of general pivot point rotation. We can understand this as a complex transformation, because we know translation, we know rotation and we know scaling. These are basic ones, and anything other than that is a complex transformation. We can call that as complex, and later we can break that up into a series of simple transformations, and then we can combine them as composite, and the composite matrix represents actually the complex transformation. So, that is what is the sequence in which we go to solve these problems. So, let us look at the example general pivot point rotation. So, we understood from general rotation that rotation is performed about origin by an angle, by some angle. So, now let us assume that there is some other point in space or some other position in space about which we are going to rotate our object. So, how do we do that is, if you look at this sequence of steps that we are going to perform, imagine there is an object like a triangle, and a pivot point position other than origin is chosen here for rotation. So, let x r comma y r be the pivot point position, which is any position other than origin. Now, our aim is to rotate the object of interest about this point. So, for this what do we do is, we first translate the pivot point so that it coincides with origin. So, the first step is a translation step. So, we are physically moving the point, a pivot point, so that it coincides with origin, and then we are performing rotation with respect to origin. So, because we are aware that a rotation with respect to origin has got the standard matrix cos theta minus sin theta cos theta 0 0 1 and 0 0 1. So, we know that general rotation, that is the origin rotation with respect to origin. So, we can simply use that matrix for rotation here, and in the third step we are actually putting this pivot point back at its original position. So, in the first step we are translating the pivot point, one translation step, one rotation with respect to origin, and then one retranslation, that is put it back at its original position. So, if we convert these three steps into equivalent matrices, what we get are three different matrices, and when we multiply them together we get what is called a composite matrix, and that composite matrix represents the complex transformation of general pivot point rotation. So, let us take the notations, and the first transformation is represented as translation T of minus x r and minus y r. So, that means we are actually making it, that is shifting the point so that it coincides with origin. And rotation theta. So, always we assume that rotations are positive unless and otherwise explicitly mentioned, like they are clockwise rotations. So, all rotations are understood to be positive. Okay. Rotation with respect to origin is then performed by an angle theta. So, that is r of theta, and by the desired angle and again put it back at its original position, which is translation x r comma y r. So, if these three are written in notation form, now you see this equation here, the new position or the point after performing a rotation for an object about a general point in space is given by the equation translation x r y r multiplied with rotation by an angle theta multiplied with translation minus x r y r. You must observe that when the steps are written in the previous order like 1, 2, 3, but here they are written just in the reverse order. You should note that carefully. They are to be written in the reverse order. First it is this from the right hand to the left hand, you should be writing the notation. So, T of minus x r y r into r of theta into T of x r y r, the red curly brace for the set of matrices multiplied with the point P, the initial point or the point that we wanted to rotate or the object that we wanted to rotate here as P. So, when you multiply these three matrices, see this here 1 0 x r 0 1 y r 0 0 1 cos theta minus sin theta cos theta 0 0 1 and 0 0 1 1 0 minus x r 0 1 minus y r and 0 0 1. So, when you multiply these three, what you get is a composite matrix and whose elements are given here as cos theta minus sin theta cos theta, and the third column has got elements which are some non-zero values x r into 1 minus cos theta plus y r sin theta, y r into 1 minus cos theta minus x r sin theta. These non-zero elements actually if you look at the first 4 elements of this matrix, they are exactly the same. If you as the original rotation matrix, that is rotation about origin, but if we are performing rotation about any general point in space, we get 2 additional elements in the third column. Generally, elements in the third column correspond to translation. That means, the point not only the objects not only get rotated about the pivot point, but also get translated by the amount proportional to these 2 elements. That is, one element corresponds to the x direction, the other element corresponds to the y direction. So, that is there is a shift, not only there is a rotation, there is also a shift. So, let us look at another case of general fixed point scaling. So, just like we did general pivot point rotation, we have general fixed point scaling. That means, imagine any point in space and perform scaling with respect to that point. It is something like you fix that point, you hold that point with your hand and let the object be pulled with respect to, let the object be resized in all directions, like say we have only 2 directions in 2D. So, stretch the object along x direction and stretch the object along y direction, but now with respect to another point, any general point in space other than origin. So, you can take an example of say a triangle whose centroid is the fixed point. Let us say its centroid is the fixed point. Then when you perform scaling, what happens is with respect to the centroid, we will be pulling the object on all sides. So, that the object becomes bigger, but while the centroid remains the same. So, for the bigger object is it is the centroid still is at the same place. But if you recollect the scaling that we did, the basic scaling with respect to origin, the upscaled object moves away from origin, while the downscaled object moves close towards origin, but in this case the object remains there, it becomes bigger in size. So, the effect is what is called a general fixed point scaling. Let us call this as a complex transformation. Let us break this up into a series of simple transformations and then let us make a composite of it, and the composite represents the general fixed point scaling. So, if you look at these scaling diagrams here, general scaling, imagine the fixed point is x f and y f with respect to which we would like to scale this triangle, and the first step is to translate the fixed point such that it coincides with origin. So, it is a translation, simple translation. Then with respect to the origin, we are actually scaling it. That means, you can upscale or you can downscale. Here in this example, it is downscaled, and the third step, put it back at the original position, put the fixed point at its original position. So, a translation as scaling and then again retranslation. So, put it back at its original position. So, if we write equations, that is notation representation for this, the first step is t minus x r minus y r, second step scaling s, s x, s y, the third step x r, y r. So, that is our x f, y f or x r, y r both mean the same here, just it is a notation. So, you can correct this as x f and y f here and x f and y f, just for a change from rotation. So, the final equation for general fixed point scaling is given by p dashed is equal to t x f y f into multiplied with scaling s, s x, s y multiplied with translation minus x f minus y f. So, see always the red curly brace, the whatever is in the braces is a set of transformations which are to be composited. So, when we multiply all the three, what we get is a scaling matrix S x 0 0 S y and two more non-zero elements in the third column x f 1 minus S x and y f 1 minus S y. So, that is how we get the composite matrix. So, this composite matrix represents the general fixed point scaling. That means, you can perform scaling with respect to any general point in space. So, here if you take origin as your fixed point, for example, so x f and y f become 0 and 0. So, now the elements in the third column become 0 and 0. So, that is how this is a more generic matrix for scaling. So, let us take another example here for composite transformations. General scaling directions. So far, scaling is being performed one along the x direction, the other along the y direction. So, we have two scaling factors S x and S y all the time. So, that means, whatever object is of interest we have with us. So, we will be scaling it along x direction and you will be scaling it along y direction as well. So, here we can also imagine scaling to be being done or can be done along other directions also. So, let us take two mutually perpendicular directions as shown here in this slide, S 1 and S 2, which are actually mutually perpendicular, but not along x and y directions, not along the standard coordinate directions. So, now there is a square. The square is an object on which we are applying a scaling transformation, and the scaling is not done now along x and y, but instead along two other mutually perpendicular directions S 1 and S 2. So, that means along diagonal. So, see the scaling factors here, S 1 is 1 and S 2 is 2. So, that means S 1 is 1 means along S 1 direction there is no scaling. So, the size should remain the same. Along S 2 direction the size is double. So, because it is scaling factor is 2, that means it is something like you are holding the two diagonal edges, two edges of the square, that is 0 0 edge and the vertex and the 1 1 vertex, and then scaling it like this. So, that the length of the edge along the diagonal is now more than the original length. So, the steps are shown here. How do we go with it? Let us call this a complex transformation. So, our aim has always been to take a complex transformation, break that up into a series of simple transformations, and then take a composite of that and then multiply the original coordinates, get the final coordinates. So, the first step is to rotate the two scaling directions such that they align with coordinate directions. So, the first step is to rotate S 1 and S 2 directions, they are already mutually perpendicular. So, rotate them such that S 1 coincides with x and S 2 coincides with y. So, this rotation is intentionally taken as positive because it is counterclockwise rotation. So, by what angle you should rotate? So, the angle is evident here, the angle is theta. So, S 1 direction makes an angle theta with x axis. So, S 2 direction obviously makes an angle 90 minus theta with x axis. Let us rotate this. Is the first step is to rotate the two scaling directions such that they align with the coordinate directions, that is S1 aligns with x and S2 aligns with y. The second step is to perform ordinary scaling with respect to origin, and third step is to rotate that back. So, a rotation, a scaling, and then inverse rotation. So, the steps are shown here: r of theta, S S1 comma S2, and r inverse of theta. So, that is actually shown here in the notation, and in the matrix equivalents for this actually are shown in the next slide. Before we go to that, let us see what is going to actually happen to the shape. So, this is the square, and this is actually a 0011, it is a unit square, a standard unit square, and now you are performing scaling on this object along two mutually perpendicular directions S1 and S2. The scaling factors along S1 is 1 and along S2 is 2, and theta is 45 degrees. So, what happens actually is, look at the resultant shape. The resultant shape is actually like a parallelogram, and it is slightly up, and is not actually, the bottom edge is not touching the x axis, it is slightly above that, and the coordinates of the except 0 0, all the other coordinates got changed for the other vertices, other 3 vertices. The 1 1 vertex has become 2 2 now, because it is twice is the scaling factor along that direction, but along the other 2, that is the other 2 vertices have become 1 by 2 comma 3 by 2 and 3 by 2 comma 1 by 2. So, this is the effect of this is actually a change in shape. So, that is what we have achieved here at the end. So, if we take an example, let us take an example problem that we can solve easily. Consider a triangle at 2 comma 2, 10 comma 2 and 2 comma 10. So, the 3 vertices of a triangle are given. Now, perform the following transformations in succession and find the resultant vertices. Now, our aim is to perform these 2 transformations on the triangle and then find the resultant position. So, the first step is to scale with respect to 2 comma 2, that means the 2 comma 2 is the fixed point with respect to which now you will be scaling the object, which is by scaling factors 2 comma 2, and the next step is rotate by 90 degrees counterclockwise. So, P dashed is equal to r of 90 into S 2 comma 2. So, we always write that in the reverse order, and the first step is scaling with respect to fixed point, which is 2 comma 2. For that, the transformation matrix is 2 0 and xf into 1 minus Sx. If you remember, xf into 1 minus Sx and 0 Sy yf into 1 minus Sy. If you remember the scaling matrix, that is with respect to any general point in space that we have just derived before, we have got the matrix Sx 0 0 Sy, xf 1 minus Sx, yf 1 minus Sy 0 0 1. So, that is what we have applied here, and we got a, if you are not able to remember this, what you can do is translate the fixed point 2 comma 2 to the origin, that means minus 2 to t of minus 2, then perform ordinary scaling, that is these 2 elements are 0 0, the scaling factors are 2 2, and perform a retranslation. You can do these 3 and still you get the same matrix as that of the fixed point scaling matrix. So, if you do not remember in any case the general fixed point rotation matrix, you can take these steps in 3 steps and multiply, get a composite, and that represents the same matrix. And next step is to perform a rotation. So, rotation is 90 degrees counterclockwise, and so what we get is a standard rotation with respect to origin, and we know the angles, that is 90 degrees is the angle, and cos theta minus sin theta cos theta 0 0 1 0 0 1. We got a resultant matrix here for rotation, and the last step is to multiply the scaling matrix, multiply the rotation matrix, get the final composite. So, do not do anything to the triangle just get the composite matrix, and the next step is to take each vertex of the triangle, multiply with the composite matrix, get the new vertex. Take each vertex one by one. There are 3 vertices. Take the first vertex, say 2 comma 2, and because that is actually you are getting minus 2 2, and the second thing is 2 comma 10, and the next thing is that is the equivalent. So, multiply here the 2, 10 and 1 with the composite matrix, you get minus 18 2. Take the third vertex 10 2 and multiply with the composite matrix, get the third vertex, new vertex here minus 2 18. So, this is how you should be solving problems. So, now we have learned here a simple sequence of steps to solve complex transformations, like take a complex transformation, break that up into a series of simple transformations, and then multiply the simple transformations in the reverse order, get a composite matrix, and have the composite matrix with you. Take each vertex, multiply with the composite matrix, get the new vertex. So, that is what we have learnt in this module. So, we have learnt how to perform composite transformations. We have also have seen examples on how to perform what is called complex transformations by simply decomposing them into simple steps and then getting a composite and then solving problems. So, you can solve any number of problems, you can take simple exercises and solve problems, and you can try for yourself all this. Thank you.